Okay, so before we get into looking at these rules specifically, let's just quickly review when we're finding the derivative. Okay, what are we actually finding? What is the derivative telling us? Slope of the tangent line. Okay, slope of the tangent line. And slope, you guys know, is a rate of change. Okay, so the slope of a tangent line, the rate of change of a function at whatever point we happen to be looking at. Okay, now when you find the derivative and you have an x still in the function, okay, you then have a derivative function. Alright, or it's the derivative in terms of x. So then you can plug in any value of x, and that gives you the slope on the original function at that value of x. Okay? So remember, that's what we are finding here. Don't lose sight of that, even though we're not doing a lot of application in this unit specifically. Okay? The other thing here is, don't forget that when we're doing derivatives, there's a lot of different ways of asking you to do the same thing. Okay? You might be asked to find the derivative or find dy dx. Okay? Remember the notation we had, dy dx. You might be asked to find y prime. If you're given f of x, you might be asked to find f prime of x. You might be asked to differentiate. Alright, all of those things are simply telling you find the derivative. Okay? That's one thing that can be a little bit confusing, but there's just a lot of different ways to express the same idea here. Okay? Of finding the derivative. So let's real quickly here, yeah.
So when you say finding the derivative, is that asking for the function or for the specific like y value when you plug in an x value?
If it does not give you a specific x, then it's just finding the function, yeah. Like if it just says find dy dx, you're just finding the derivative function. If it says find the slope of the tangent line or the gradient of the tangent line, or it might say find f prime of 3, then you're finding f prime of x and then plugging in 3 for it. Okay, so yeah, good question. So let's look at these basic rules, and then we'll let you guys practice with some of this. Okay, so first of all, we have the derivative of a constant, and you guys can see here that it says that the derivative of a constant is 0. Now, if I have f of x equals 5, what does that look like? It's a line, and specifically it's what kind of line? Horizontal. It's a horizontal line. What's the slope of a horizontal line? 0. Alright? So, that is why the derivative of a constant equals 0. Because no matter where I am on that function, if I have a horizontal line, it doesn't matter if x is here or here or here, the slope is always going to equal 0. Okay? So, that's our first rule. So if I have the function f of x equals 5, then f prime of x equals 0. Okay? So that's our first one. That's a pretty easy one. The second one is probably the most commonly used one of all of them, and that is differentiating x to a power. X to a power. Now you can see there, x to the n becomes nx to the n minus 1. Can someone put in their own words what's happening here with this rule, Josh?
You take the exponent and you make it into a constant, so constant. You basically
coefficient?
A coefficient, like you attach it to the variable, so it's a coefficient, and then you just put it as an exponent, but minus 1 of what it was.
Okay, so you take the original exponent, make that your coefficient, and then subtract 1 from the exponent. That's all you're doing. So if I have x to the 5th, I'm going to make 5 the coefficient of x, And now x, instead of being to the 5th power, is going to be to the 4th power. Okay? Now, part of the reason why I said this is one of the most commonly used ones is, for one, we do a lot of polynomials, but also, it's not just for things like this. It actually works no matter what n equals. For example, let's say I had f of x is the square root of x. Well, how could I write that as x to a power?
X to the 1/2.
Yeah, very good. X to the 1/2. So now I have x to a power, and if I want to take the derivative of that, I bring it out in front, 1/2 times x to the, what power would I have now?
0. No. Negative 1/2.
Negative 1/2. Okay? Negative 1/2. Now, a little rule about simplifying. With IB, okay, this isn't like a standard rule, this is just something that I've recognized is typically about how far they take it. Always simplify negative exponents. You do not need to make fractional exponents into radicals though, and you do not need to rationalize. Okay? So, for this, we would make this 1 over 2x to the 1/2. If you want, you could make that 1 over 2 root x. You do not need to, and I would actually recommend that you not go any further than that. Don't make that like root x over 2x. You know, multiplying by root x over root x or something like that. I would not go that far. Okay?
Okay.
So, that's another application of this power rule. Alright? Another one would be a function like this. Let's say we have f of x equals 1 over x squared. How would I rewrite 1 over x squared as x to a power?
1 over 2x.
No?
X to the -2.
There we go, Adam. X to the -2. Okay? X to the -2. Now I have x to a power, so I can take the derivative. F prime is -2 times x to the what power now?
Negative third.
-3.
Yes, good. That's a really common mistake. Folks will they'll be going too fast and they'll make the 2 a 1, forgetting that, hey, we're in the negatives and we got to subtract. Okay, so it's -3. And then I would rewrite that as -2 over x cubed. Okay, we should simplify that to -2 over x cubed. Okay, so this power rule, it shows up a lot. We use it a ton. By the time probably we're done by today, you'll be doing it without even really thinking too much about it. Okay, it's just once you get the hang of it, it's pretty easy. Okay? Alright, so now we have kind of extensions of this power rule, and that is, what do we do when we have a constant times a function? So here it's not just x to the 5th, it's 6 times x to the 5th. And for that, it's simply you take the constant. Whoop, how did I get on? There we go. You take the constant, and we're going to take the derivative of the function just as we normally would. So the derivative of x to the 5th, we already saw, was 5x to the 4th. And we're simply going to multiply that by the constant. So 6 times 5 is 30. We have 30 x to the 4th. Okay. So again, not too hard, but you just have to keep track of everything. Notice here, when the constant is multiplied, it doesn't become 0. Okay? It's only when you have a constant by itself and take the derivative that it becomes 0. Okay? So finally, we have the addition rule, and this is really where we're going to be able to apply all three of the rules we just learned to be able to handle any kind of polynomial, and even some things that aren't polynomials. And that is this addition rule. The addition rule says that if you have two functions added together, you can simply take the derivative of each one separately and add those together. Okay? We saw this with limits. If I had the limit of a bunch of stuff added together, I could take the limit of each one separately and then add those limits together. Okay? If you remember though, a derivative is just a big limit. So the rules that applied for limits carry over and apply here too. Okay? A lot of them do. So if I'm going to take the derivative of 3x squared plus 7x root x, or plus 7 root x minus 9, I'm going to take the derivative of each of these parts. So the derivative of 3x squared with respect to x is what? 6x. 2 times the 3 is 6. 2 minus 1 is 1. So it's 6x to the first. Okay? So now I know down here f prime of x is 6x plus something. So now I'm going to take the derivative of 7 root x. Okay? Well, I already found that that the square root of x has a derivative of 1 over 2 root x. So since I have a constant, I'm just going to take 7 times 1 over 2 root x. Okay? And I can write that as 7 over 2 root x. So now I know that the f prime of x is 6x plus 7 over 2 root x. And then what's the derivative of negative 9? 0. It's a constant. Okay? So I'm done. This is the derivative of that function with respect to x. 6x plus 7 over 2 root x.
Couldn't you simplify 7 over 2 root x, or should you just not?
How would you simplify that?
You would just divide the 2 out, so it'd be 3.5 over root x.
You could. We typically don't do that because we don't like to leave complex fractions, fractions with fractions inside of them. So it wouldn't be mathematically wrong, but... And by the way, guys, that's another thing that if you're asked to find the derivative, I do expect you to simplify like the negative exponents and that sort of thing. However, if the problem is simply asking you, hey, find the slope of the tangent line at this point, I don't care how much or how little you simplify the derivative itself, because the whole point is to get that slope at the end. So if I got to something that had the negative exponent in it, I could go ahead and plug in x right there and not risk making a mistake in my simplifying or something like that. So that's where understanding the context of the problem is important. You may or may not need to simplify like we normally will. Okay? So, all right. So at this point, I've given you some practice that we're going to work on now. These first few are just some very basic ones. One thing though, looking at number 3, you're going to need to rewrite these. Okay? For example, right now we don't have a way to do the derivative of a function times a function. We're going to learn the product rule next week. Okay, but even if we knew that rule, this one, part B here, is a lot easier if we rewrite it. Okay, how could I rewrite x times the square root of x?
Can you do x
Times
minus
x to the
1 over x squared root 2? Yeah.
Okay, x times x to the 1/2,
Yeah.
which is what?
1/2 radical x. Oh, you
No.
mean that. Oh, I thought you meant the x 1/2.
Oh.
Three over two.
I thought
X to the
I thought it was
three
1
over
over.
X to the 2.5.
X to the 3/2 or 1.5, okay? So x to the 3/2 power. This is x to the first. You just add the exponents, right guys? So 1 plus 1/2, so x to the 3/2, okay? And just to avoid confusion, since we're already writing pretty small, we typically use improper fractions. It's not right or wrong, but just to avoid mistakes. A lot of times we'll do that. Another thing, things like this. We don't have a way to do a function divided by a function. However, since I have a monomial here on D as my denominator, I could split this up and I can reduce each of these, and then I'll have something I can use my rules for, okay? Or like h, what would I want to do with h before I try to in the derivative? Distribute the x and then FOIL, okay? I need to multiply it all out at this point in order to find the derivative, okay? So, some of these you may have to manipulate a little bit first before you can actually take the derivative.
Quick question.
But yeah.